Hey, this is Michael. Today we're going to cover a SPI Master. And I know there's a lot of stuff on the internet and on YouTube that goes over the implementation of a SPI Master that covers the SPI protocol in detail. I'm going to start with a fundamental question. Why would you bother to code your own SPI Master when the major FPGA vendors all provide SPI Master as free IP? Example, Xilinx offers the XE Quad SPI. There's your block diagram, easy to find online. Altera Intel offers their SPI Master, probably an Avalon interface there. Easy to find documentation on that. And even Lattice Semiconductor provides a SPI Master. All right, so with all this free IP out there, why are you going to code your own SPI Master? Well, a few reasons. Let's stop there. One, these SPI Masters, they're like the Swiss Army knives of SPI Masters. They do everything. And as a result, they're very complex. They usually have a complex register set. You have a fairly large document to cover. I know that they're simplified because they're supported by a board support package and so forth. But there's a lot of overhead to using somebody else's IP as a SPI Master. So portability, once you've bought into using Xilinx, Altera, Lattice's IP, you're stuck with them. Okay, you can't take that SPI Master and switch sides. Modifiable. If you've written your own SPI Master, you know how to modify it. And simulatable. Try simulating one of these pieces of IP. It can be done, but there's a lot of overhead in setting up the simulation libraries and so forth in order to simulate the XE Quad SPI or these various SPI masters provided by the FPGA vendors. So let's have a quick look at a SPI master that I've put together and I've been using for a while. All right. So there's the port. It's written in Verilog. There's the port list. Let's start with the parameters. So I have three parameters here. One parameter sets the data length. Now, I know a lot of implementations handle byte-wide data. A SPI is not a byte-oriented protocol like I2C. So you'll see a lot of devices out there that aren't exactly 8 or 16 or 24 bits. They're somewhere in between. So data length, the number of bits you're going to shift out and thus shift in, is a parameter. S-clock delay is how I handle the S-clock frequency. So the S-clock frequency is going to be essentially set by the state clock, this clock input. It's going to be set by a certain number of clock periods. For example, if state clock is running at 100 megahertz, the minimum S-clock frequency I can support is 50 megahertz, half of that, where S-clock is set high for one state clock period and low for one state clock period. If S-clock delay is 0, that's what we get. If S-clock delay is 1, we're going to dwell on S-clock high for 2 clock periods, and we're going to dwell on S-clock low for 2 state clock periods. So that's going to essentially half the frequency from 50 to 25 megahertz if your state clock is 100, and so forth. All right. And then mode, there are plenty of implementations that support all 4 modes. I'm lazy. Most of these simple SPI devices are just mode 0. I've seen a few that do others, and I support them as needed. All right. So the SPI Master, as it should, supports both reading and writing at the same time. For every bit that's shifted out, you shift the bit in, and so forth. At the end of the access cycle, after having shifted all bits out and in, the data that's been shifted in appears on read data. And I'm just going to quickly read my notes here. The busy output is high while the access is going on, so while the bits are being shifted out and so forth. Uh, Most DACs, and then we're talking simple SPI devices, most DACs are write-only devices, so we don't read. Likewise, most ADCs are read-only devices, so we don't write. In the case of a DAC or a write-only device, uh, we don't need the MISO input. We can just tie that high, and we can leave the read data output unconnected. In the case of an ADC, which is a read-only device, we can just set write data to all zeros, and we can leave MOSI unconnected, and so forth. And your synthesizer will just optimize out the unused logic. All right. So the actual implementation in Verilog is just a state machine with 6 states. Right? We stay in the idle state until the start access signal is asserted high. We transition to CSN low state where we assert the chip select and so forth. So let's go through what's happening as we transition through this state machine. And that's best viewed in a simulation. So here I have a snippet. Oh, that didn't work out. There we go. I have a snippet of a simulation that was done in Altera's free version of Model Sim. Uh, and so what we see here is we see the state machine in state 0, which is the idle state. And it will stay there forever until the assertion of start access. So here we see we've driven write data with hex value 248. We assert start access, and boom, we transition to state 1, which is state CSN low. And at that point, we drive CSN low, the chip select or slave select, and we also drive the first bit of the write data, the most significant bit of write data. And that's done by setting bit count to 9. So here in the simulation, I've set my data width to 10. All right, so we're starting with index 9, and index 9 is causing the most significant bit of write data to be driven onto the MOSI pin. All right. Then we transition to state 2, which is clock high, and then to state 3, which is clock low. And on the transition from state 2, clock high, to state 3, clock low, not only do we deassert S clock, but we also increment the decrement the bit count, causing the next bit of write data to be driven out onto MOSI. And that sequence repeats, going from state clock high to clock low, clock high to clock low, and decrementing the bit counter until we get down to the bit count 0. And at this point, from state 2, clock high, we transition to state 4, which is clock low end. And why do we do that? Well, it's because we do not want to decrement the bit count below 0, and because we want to wait 1/2 S clock period in that state before deasserting chip select. So in state 4, which is the clock low end state, we're just counting out S clock cycles. S clock counter is counting the number of state clock cycles we dwell on each state of S clock. So we're 3 state clock cycles while S clock's high. We're 3 state clock cycles while S clock's low, and so forth. So at the end of state 4, we transition to state CSN low. Can't see that there, but there it is. Sorry, CSN high, state 5. And then at that point, we also latch the contents of the input shift register that's been capturing the state of MISO. We latch that onto the read data output. And then we wait in this state until the the start access signal's deasserted. Since it's already deasserted, we don't spend a lot of time in that state, and we transition back to the idle state. So there we go. 6 states. We've implemented our little SPI Master state machine. And this works for, uh, in my opinion, the majority of these simple SPI devices. So let's have a look at some of these devices. And just say that these devices, I'm not going to show you the whole data sheet. We'll just get lost that way. But they typically have a waveform that shows the timing of the SPI interface, as well as a second waveform that shows the protocol, shows the locations of the various control and data bits within the number of bits that are being shifted in. All right. So let's have a look. This is a microchip DAC. And here we're looking at the timing waveform. And what I'm really interested in, there's a lot of information there, but I really want to know what S clock, its maximum frequency is. So I'm just going to scroll down. I've captured the AC timing characteristics, and there we go. For all voltages, all across all temperature, the frequency, the maximum frequency of S clock is 20 megahertz. Okay, and then we'll scroll down here, and I can see that, okay, this is a 16-bit SPI device. All right, so we'll want to shift 16 bits in, and we'll allow there's some other intelligence to set up the actual data. We're just taking care of taking 16-bit data in and shifting it out in mode 0. We can see this is mode 0 here. Chip select starts high, S clock starts low. All right. Now there's another tweak on this, and because this is a dual DAC, they have a load DAC input, which will have to be handled outside of the SPI master logic. The reason for this input is simple. It's because it's a dual DAC, or it could be a quad DAC. The load DAC allows you to go ahead and update both DACs internally, and then by toggling load DAC, both outputs or all outputs update simultaneously from what was configured in the register. All right, so let's go through how we set up the parameters, the S clock delay, mode, and data length. Well, I've shown you data length. It's easy to see. This is a 16, so we're setting data length to 16. This is mode 0. We can clearly see that, so we're setting mode to 0. And how do I set up S clock delay? Well, the frequency of the state machine divided by the frequency of S clock is 5. Okay, so we've got to run it at 1/5 of the state machine frequency. All right. Now, the way I've set up the logic, I can only handle multiples of 2. So the next multiple of 2 above 5 is 6. And the closest S clock frequency would then be, instead of 20 megahertz, it's going to be 100 megahertz divided by 6. We're dwelling on S clock for 3 state machine cycles high, 3 state machine cycles low, for a total 6 clocks or state machine clock cycles per S clock cycle. And S clock delay therefore becomes a value of 2. All right, so we've got all 3 parameters, and we're done. We've configured our SPI master for this particular peripheral. All right, let's go have a look at another one. So here's an 8-bit DAC. Once again, it's a write-only device. We have our chip select, we have our S clock, and we have, looks like this is another 16-bit peripheral. All right, so what concerns me is our S clock period, or S clock frequency. Period of 100 nanoseconds corresponds to 10 megahertz. All right, so let's go figure out how to set up our parameters. So 100 megahertz divided by 10 is 10. That's already a multiple of 2, so I don't need to round it up to the next multiple of 2. And therefore, our closest S clock frequency would be spot on 10 megahertz. So I'm going to set the S clock delay to 4. So we're going to get we're going to dwell on um, uh, the state machine clock for 5 clock periods while this clock's high and 5 for low. It's mode 0. I can clearly see that from here, and the data length 16. All right, so we've set up that guy. And one more, actually maybe two more. I think one more peripheral. Now this is an ADC. All right, so this is a read-only device. We're not driving MOSI. We're just looking at MISO. So there's our timing. I can't tell. It looks like it's a mode 0 based on clock being low, chip selects high. I can't tell how many bits it is quite yet, but let's have a look at the timing parameters. All right, and this guy's, he's a slightly different animal. He's pretty slow. Okay, so hey, let's say we're going to run this guy at 3.3 volts and not at 5. So we've got to take this as our maximum S clock frequency, about 1 megahertz. And then looking at our little protocol timing diagram, I can see that this is 12 bits. I've got bits 0 through 10. And then if we work our way back, we see is that right? Do I need to do another count? No, I believe this is, I thought I had this down. 10, it's 11, 12, 13. Can you believe it? 13 bits. Okay, so I had that wrong. Data length 13. Okay, so 100 megahertz, our state clock frequency divided by S clock frequency gives us 95.24. Rounding up to the next power of 2 is 96. Our closest S clock frequency would be 100 divided by 96, so 1.042. So we're going to be able to not exceed our maximum timing with that value. So we set up our S clock delay. 96 divided by 2 is 48, minus 1, 47. So that's what I'm going to set S clock delay to. Mode is 0. Data length, oh, I can't change that because this is a PDF. Okay, so data length is nebulous here, but I think it's either 12 or 13. All right, so we've set up another one. Here we go. Here's another ADC. And we've got it all in one here. So we've got our timing as well as our protocol. So I can see that this guy is actually a 14-bit peripheral. Okay, so you've got 12 data bits, and then we've got 2 filler bits. And it looks like it's using these first 2 clock cycles to kind of kick off the conversion. And then the remainder allows you to shift out the converted data. So let's have a look at what our maximum S clock frequency is. And I don't know why I got that. Okay, so FS clock, so maximum is 16 megahertz. All right, let's go with that. 100 divided by 16, 6.25. Next multiple of 2 gives us 8. So we can run our S clock at 12.5 megahertz with our 100 megahertz sample clock. And then our S clock delay becomes 8 divided by 2 minus 1 is 3. It's mode 0, and the data length is 14. There we are. So we've taken the same SPI Master, and we're able to support these 3, 4 different simple SPI devices. All right, I'll do one more. Might be overkill, but this is an IO expander. It's got this data sheet's a little painful. I don't think they tell the whole story, but here we go. So from here, there's our timing. We'll scroll down and look at, so let's just say we're going to run this guy with 3.3 volts. So we can use the 10 megahertz as the maximum S clock frequency. And let's skip this for now. We'll come back to that. But we've already done the math, so we know that S clock delay is set to 4 to get an S clock frequency of 10 megahertz. It's a mode 0 peripheral. We saw that in the waveform. And then let's come back to this. In 16 bits here, we have an opcode with a read-write bit, and then we have an 8-bit register address, but no data. So there's something wrong with this picture. After looking at the register map and the data sheet for this device, I can see that it takes 8-bit data. So it looks like you need to shift in at least 24 bits to do a register write or a register read. Okay, so the first 16 bits will be the opcode and the register address, and the next 8 bits will be the 8-bit data that's written to the register address. Likewise, for a read, the first 16 bits. Now this is set to the bit level needed for a read. The first 16 bits tell it what register you want to read, and then you need 8 more clock cycles to clock in the 8 bits from the register that you're reading. Okay. So based on that, I'm setting data length to 24. I'd go ahead and prototype this, make sure you're right. Okay, so we've covered some simple SPI devices with our simple SPI Master. Now, the SPI Master does not operate on its own. You're going to need a host, usually a microprocessor that's implemented inside your FPGA. And that host needs an interface to that SPI Master. And that's usually a set of control status registers. What I like to use a set of control status registers that are an advanced peripheral bus slave. And that isolates my design, my logic from the SoC internal bus architecture of the FPGA vendor, where Xilinx AMD likes to use AXI, where Altera Intel uses Avalon Bus, and Lattice Semi uses I don't know what, because I haven't worked with Lattice in a while. But all of them have a bridge between their internal bus and advanced peripheral bus. And then by coding up your control status registers as an advanced peripheral bus interface or a slave device, and then interfacing those to your SPI master or masters, you make your design portable and independent of the FPGA vendor's IP. All right, hope this helps. Let me know if you like it or don't. Hit like if you like it. Give me a comment if you don't. Take care.